All right, so now here we're gonna do a revision on the functions. I'll try by all means again to touch on the basics as much as I can. And yeah, let's start. So it's important to understand that we have four types of functions. We have the linear function, we have the exponential function, we have the parabolic function, and we have the hyperbolic function. And we need to know that for each and every equation, it has its own variables. And you need to know each variable, what is the meaning of each variable from the equation. And do not forget, it's either they give you a sketch, and from this sketch, you use that sketch to determine the equation of that graph that they drew for you on the sketch. Ne? Or it's either they give you the equation and they ask you to do what? It's either they give you an equation and they ask you to draw a sketch of this equation that will be provided to you, right? And of course, we need to know how to analyze the functions. It's not about drawing, it's not about determining the equation. And there are these questions that are called the deductions. So those type of questions, guys, I really need you to understand that those questions, they also apply on the trigonometric functions. They do not apply only here on paper number one, which is the functions. Ne? So deduction questions are those type of questions where they will ask you, determine the values of x where g of x is greater than 0, or determine the values of x where g of x is greater than f of x. It depends, sorry, what is given that time. But you will see the deduction questions are always there. I will tell you when I get to those questions. So I want us to start with this question, right? Having a look at this question, we have two functions. I said there are four types of functions, but having a look at what we see here on the board, we have two functions, right? The first function, which is the function of f, it is the hyperbolic function. And the function of g, it is the exponential function. So meaning this question is all about hyperbolic and exponential. So that means the parabola and the linear function, those basics, let's just put them aside for now. You understand? Right. Before I can even go through these questions, I want to remind you of something, ne? Based off the basic. Now, for hyperbolic function, remember, oh, where's my pen? For hyperbolic function, I'll just write h, ne? For hyperbolic function, the standard form or the general equation that we use for hyperbolic function, it is y is equals to a over b, not bx. We have a over x plus q. It does not matter. I understand. Sometimes you'll be like, here it's q, here it's p is what? It really does not matter. As long as you know where is the variable placed. They can even write z. They can write w. It does not matter, by the way, okay? But I know you guys are used to p and q, right? X plus p plus q. This is a hyperbolic function, right? So now you need to know what are the importance of the variables that we see over here. X and y, we know we use them for coordinate system, meaning it's given by x is to y. This for coordinates, so x and y. And then when we talk about the a, it determines what? It determines the shape of the graph. It determines where we're going to draw the arms of the hyperbolic function. Remember, the hyperbolic function, it could be like this or like this, or the hyperbolic function, it could be drawn like this or like that. So the value of a, it determines, where are we going to draw these curves of hyperbolic function? Are we going to draw the curves in the first quadrant and third quadrant of the Cartesian plane, or we are going to draw the curves on the second quadrant and the fourth quadrant of the Cartesian plane? So the value of a, it determines where are we going to draw our graph. So when the value of a, when the value of a is greater than 0, that means we are talking about the positive value of a. So when the value of a, it is positive, we're going to draw our graph here on first quadrant and third quadrant. But when the value of A is less than 0, meaning it is negative, then where are we going to draw our hyperbolic function? We're going to draw our hyperbolic function in the second quadrant and the fourth quadrant, whereby the value of A, it is less than 0. It does not matter whether the value of A is 2, it's 3, it's 4, it's 0, comma what. It does not matter. What matters for now, right now, is know the sign of the value of A, whether it is a positive value of A or it is a negative value of A, so that you can determine where are you actually going to draw your function. Are you going to utilize first quadrant and third quadrant, or are you going to utilize your second quadrant and the fourth quadrant? That will be determined by the sign of A. So now we are done talking about A. Let's talk about P. So what does P actually talks about? I'm not going to talk about P only, but I'm going to combine it with Q. So when we talk about the value of P and Q, we are actually talking about the asymptotes, okay? So we are talking about the asymptotes. When you talk about the asymptotes, asymptote, it is a line that our graph actually approaches. Our graph do not cut the asymptote. Our graph do not touch the asymptote, but rather our graph will always approach the asymptote. So now having a look at this function over here and this function over here, where we will assume that the value of A, it is negative, which is less than 0. Ne? Our asymptote for this function over here, it's given by this line over here. For this graph, you can see that this graph, this curve, it approaches the asymptote. It doesn't touch the asymptote. It never touches the asymptote. It never crosses the asymptote. It does nothing but only approaching it. So meaning this asymptote, by just looking at it, it is the value of y. So this is the y asymptote, or we say it is the horizontal asymptote. So the horizontal asymptote of the parabolic function, it is denoted by the value of q. Okay, so the value of q, it denotes the horizontal asymptote. Now again, looking at the very same function over here, again, we can see that our graph, again, it approaches this line, which is this line over here. This line, having a look at it, it represents the x value, right? Whereby the x is equals to 0. So here we have the vertical asymptote. And from the equation, the vertical asymptote, it is actually denoted by P. Our vertical asymptote will be actually denoted by P. That's it about the basics of hyperbolic function. Oh, let me not forget this, which is most of the times students tend to forget. But for now, based off the equation provided over here, I just wanted to explain for each and every variable that we see on that equation, what does it actually mean? What does it actually explain? Okay, so that's just how it works. Now, I want to talk about few analytics of hyperbolic function, on how to analyze the hyperbolic function before. Remember, guys, we'll do the questions. Right now, I just want to get your basic on track before we can solve this question, so that you can see how I solve these questions relating the basic that I have just taught you over here. Okay, so now let's talk about the analytics. Yeah? I want us to talk about the analytics. I want to analyze the hyperbolic function. We're going to use the sketch rather than using the equation. Eh? So say for an example, we have a parabolic function just like so. Here's our Cartesian plane. We know that here we have the x-axis. We know that there we have the y-axis, right? Right. Now let's assume that our hyperbolic function, it has the asymptote. It has the asymptote x is equals to 0 and the y is equals to 0. So that means our graph will look like this. And let's assume that the value of A, it is less than 0, meaning it is negative. You can just look, you can just It's happening there. The value of A, it is basically less than 0. We can just see from the graph that, we utilize the second quadrant and the fourth quadrant of our Cartesian plane. That's why we say the value of A is less than 0. Okay, sure, fine. We have already spoke about that. Now, the analytics that I want to talk about is what we call the axis of symmetry. Okay, let's talk about the axis of symmetry. So when we talk about the axis of symmetry, what are we talking about? Now, this is a hyperbolic function, and I want to tell you that the hyperbolic function, it is symmetrical. What do I mean when I say the hyperbolic function, it is symmetrical? Meaning, something that is symmetrical, you can cut it into two equal halves, right? For an example, if you have a circle just like this, a proper circle just like this, and then you cut it just right in the middle, we know that this circle or this shape is symmetrical. It is not asymmetrical, but rather it is symmetrical. Do you understand? So now, having a look at this hyperbolic function, the hyperbolic function, we say it is symmetrical about the origin, okay? Always know this, the hyperbolic function is symmetrical about the origin, okay? Okay, let me prove to you what do I mean when I say it is symmetrical about the origin. Now, here's our hyperbolic function. And then remember this dot over here, this center over here. What's happening now? This thing over here, what does it call? It's called the origin, whereby the coordinate is 0 is to 0. So now, when I draw a straight line, just like this, when I draw a straight line, just like this, I hope you can all see that. By the way, let me change the color. It seems like that one, it's not clear. This is the origin. And then we have the straight line that passes through the origin like this. What happened? What is happening? Our graph it is equal, right? We managed to cut our graph into two equal parts. We have this upper part. We have this upper part. Can you see it? And we have this lower part. So that means we managed to cut our graph into what? Into two equal parts. So that means hyperbolic function, it is symmetrical along what? Along or about its origin. You understand? And then again, it's very important to understand this. This line over here that cuts our graph into two equal parts, it is a straight line. Now this is where we introduce the linear function inside of the hyperbolic function. This line over here, it is given by the equation y is equals to mx plus c. You get it? We have the hyperbolic function, and inside of the hyperbolic function, we have just introduced the linear function. Why? Because we literally have a straight line equation. We have the straight line. It has equation as well, that straight line. Now, having a look at this, always know this, ne? The gradient of the gradient of axis of symmetry is equals to 1 all the time. Ne? It only depends whether we have the positive slope or the negative slope. Looking at this one, remember guys, I think I have already spoke about this. If you have a Cartesian plane just like this, and if you have a Cartesian plane just like this, I want to talk about the positive and the negative gradient. Starting from here, moving like this. Remember, this is y-axis and x-axis. This is the steep. You are going up the steep. I've been saying that someone would say, why don't you say Abu Disebo? We start from here, we move downwards, we are moving down the steep. And I say to them all the times, you start from the y-axis. You don't start here and move down. You're supposed to start from the y-axis and then you move along your line. So we see that starting from this line over here, which is y-axis, we are moving up the slope. So when we move up the slope, or maybe let's say you want to go up the steep, maybe it's a competition. If you have people who support you, they will be saying, Tshepo, Tshepo, Thando, Thando, Lebu. Meaning, those people, they are giving you positive motivation, right? Because they know steep is not a child's play. It's not easy for you to climb the steep, but those people will be there giving you positive motivation. So when you move up the slope, just like how we see over here, we say this slope, it is positive because those people, they will be giving you a positive motivation to climb the slope. So having a look at this graph over here, we can see that it is a straight line, but the gradient or the slope or the steepness of this graph, it is positive. So that means if I were to rewrite this equation, substituting the value of m, I would say this equation is y is equals to positive 1x plus c. Now I know that my gradient is equals to 1 over there. You understand? So this axis of symmetry, it is given by this equation over here. It is also a linear function, right? Right. The magnitude will always be 1. It's either we have positive 1 or we have negative 1. Here we can see we have positive 1. So the reason why I'm saying we can also have negative 1 is because we do not have only one axis of symmetry. We have two axes of symmetry when it comes to the hyperbolic function, okay? So another axis of symmetry is going to move like this, okay? Let's say maybe the yellow one, it is not there. If the yellow one, it is not there, therefore we're going to have the one that moves like this. This, it is also called the axis of symmetry. It cuts our graph into two equal parts. Let's assume the yellow one, it is not there. We have only the blue one, right? This is also called the axis of symmetry. But look at the gradient of this axis of symmetry. Remember, you start from the y-axis. You start from this line, right? You start from this line. It does not matter whether you start here, you start here, it does not matter. Let's start here. How is this line moving? Is it moving up or down? It is moving out, down the slope, right? We start from here, we move down the slope. So when you move down the slope, do you need a positive motivation to move down the slope? No. I mean, like, people could be negative towards you and say, now you won't make it till down there. You won't make it. It's like, I mean, like, look, you don't care about the negative motivation because it's not like you need more energy to move down the slope. It's easy to move down the slope than climbing the slope, right? So here you just need the money. Even if they give you negative motivation, you will move down the slope. So that means a slope that looks like this, we say it is negative slope, right? So that means the equation for this graph over here, which is a linear function, it is given by y is equals to mx plus c. But what is the gradient of this slope? I'm saying to you, the gradient of axis of symmetry will always be equals to 1, right? But here, look at the gradient. Look at the gradient. We say the gradient, oops, sorry about that. We say the gradient is going to be equals to 1. But the slope, it is negative. The gradient, remember, gradient, slope, steepness is the same thing. Gradient, slope, and the steepness, it is the same thing, same terms. They mean the same thing, okay? So meaning the gradient here is going to be negative 1. So that means the equation here is going to be y is equals to negative 1x plus c. Therefore, this will be the equation of this axis of symmetry. Okay? I hope that is clear. I haven't spoke about the shifting of the asymptote. I haven't spoke about the deductions, but that I will do it when we solve the questions, when we come across those kind of questions, okay? I hope everything was clear. So let's see if we're gonna be able to solve these questions. Are we guys on the same boat? Do we all understand so far? What am I saying right now? What I've just said.
Yes.
Okay.
Yes.
All right. Now, let's start here with question number 6. Oh, I haven't spoken about, okay, let me do the basic for this one. It's fine. I haven't spoke about this one. Okay, it's fine. Let's talk about the exponential function. The exponential function, it is noted by what? It's gonna be easy to answer the questions if you know the basic. Trust you me. One question is enough for you. For functions, as long as you know the basics, one question is enough for you. You would solve the functions for the rest of your life. So now, the exponential function, now we move to exponential function, is given by y is equals to a b to the power of x. Actually, here it is plus p, by the way, plus q over there. But normally this plus p, it is highly investigated in grade 12, whereby we're gonna talk about the inverse function of the hyperbolic function. Okay, it's highly investigated in grade 12 than in grade 11 than in grade 10. Even grade 10, we don't even have p, we don't even have q. It's just like the simple function. But yeah, it's fine. So now when it comes to the exponential function, ne, remember x and y, we know what they do. Coordinates. X is to y for coordinate system, right? We killed that, we spoke about it. um let's talk about the value of b. Let's start with the value of a. The value of a, it talks about the dilation of your function. Do you understand? It talks about the dilation of the function. If you have a exponential function just like this, let's say you have exponential function like this. Let me draw another one so that we can compare them. Say again, we have an exponential function that looks like this. Having a look at these two graphs, they are different, right? They could be the same, but the value of a for this graph, like it could be y is equals to, let's say the value of a here is 1. So I'll just say 1. Let's say b it's 2. Does it make sense? Yes, it makes sense. B is greater than 1. Okay, let's say b is equals to 2. Let me do this. I want us to talk about this function, ne? Between 0 and 1, this side, and then yeah, let's say it's 2 to the power of x um plus 0. And then let's say this function is going to be y is equals to let's say the value of a here is 3 multiplied by 2 to the power of x. There we have 1. It is invisible. I don't have to write it, but okay, it's fine. Let me just write it. So 1 here, it represents the value of a, and then we have b to the power of that exponent there. Q is 0 as well, so it's not necessary for me to show it. Right. Let's say our functions are like this. What's different? The functions are the same, right? The difference is the value of a, right? The value of a for this function is 1, and the value of a for this function is positive 3. Look at this graph how I draw it, and look at this graph how I draw it. Meaning the value of a, it determines how far is my function from my y-axis? How far is my function from the x-axis? Remember, here it's a little bit close, but here it's far apart from each other. Meaning it determines the dilation. It determines how is my function dilating from the axis, whether a y-axis or a x-axis. So that's what it does. But most of the times, they don't talk about the value of a that much. You just need to calculate, and that is it. But for your own reference in future, if you want to know what does the value of a, I think there was one question, I can't remember. I once did a question like this back then, where they spoke about the dilations when we spoke about the transformations. But it's fine. Just know that the value of a, it determines the dilation. How far is it from your x-axis and the y-axis? The more the value of a increases, you can investigate that. I used to do that back then when I was learning my functions, because I wanted to understand the basics of the functions. I will give you that task. Okay? Do this. Take this graph, take this graph, take this graph. I used to do this when I was practicing, when I was in my time. Draw all of these graphs on the same set of axes, and you will see what's going to happen. You will see, uh, change the color. Maybe this one use blue, this one use green, this one use black, maybe this one use red. You will see, okay, these graphs, they're going to change they're going to look like this. You're going to see something that looks like this. You see, they will just change. They will just dilate, move far apart from this. You will see. That's what the value of A does if you want to investigate it by yourselves. Okay? So, yeah. So that's what the value of A does. Like I say, they don't ask much about this. Okay? They don't ask much about this. Right. Nonetheless, let's continue. So, let's talk about the... Okay, I want to erase here. Right. The value of A, do not forget, it talks about the dilation. Ne? From and away, X and Y exist. That's what it does. Ne? Now we spoke about this one. Now let's talk about... Okay, I'm not going to talk about P. Ne? You know what does P do? Ne? If you have a graph like this, let's say our asymptote is positive 1. It's Q. This is the value of Q, right? Already I'm talking about it. But the inverse function of this in grade 12, it's going to be like this. The inverse function of this graph is going to be like this. If this graph of f, this will be the inverse of f, right? Now look at your asymptote. Your asymptote will now come here. It represents p. It is no longer q. It's the same as this value of p over there because you had to interchange the value of x and y. So in a nutshell, that's what the value of p normally do. It's more focused. It's more on the inverse functions than on the straight functions. Understand? So hence why I'm saying for now, I'm not going to talk about it for now only. Right. So now, oh guys, I love functions. Functions is my favorite. So now, let's come here. Let's talk about the value of Q. Q is simple. It's an asymptote. It's an asymptote. It's an asymptote. So hyperbolic, not hyperbolic. Exponential function has only one asymptote, right? It does not matter what is the numerical value of that asymptote. It could be 1, could be -1, it could be 0. It really does not matter. So we saw that the asymptote, if we draw it like this, our asymptote will be this line over here, the x-axis, whereby y is equals to 0. Or if maybe we put our asymptote over here to be positive 1, our y will also, this is x-axis, our y here will be positive 1. So this will be, oh, let me not touch the asymptote. Let me approach it. This will be our asymptote. Just like how I explained under the hyperbolic function, the asymptote, it is a line that the graph approaches. You see, our graph, it approaches it. It doesn't cut it. It doesn't touch it. It doesn't cross it. It approaches it. Even when you draw these graphs, make sure that your graphs, you approach your asymptotes. Ne? So that's just how it works. What else am I missing? Oh, the value of B. Yeah, now the value of B is very important. Now the value of B is very important. What does the value of B mean? So this is where I want you to focus. Ne? The value of B is very, very important. That's why I wanted to end with it. Now, if you have your, I'm gonna draw two graphs. Ne? Let me show you something. Let me draw it here. This will be my Cartesian plane, right? And therefore this will be this, right? And therefore this will be our y-axis, and therefore this will be our x-axis, and this will be the origin. Now let's say I have a graph that moves like this, right? This is my exponential function, and it approaches the asymptote. Let's say this is the asymptote, right? This is the graph. Now let's talk about this graph. Ne? We know everything about this. Why is this graph shaped like this? This graph is shaped like this because the value of B is greater than 1. Here, if you talk about both negative here and the shape, that will be the inverse along the x-axis. I'll tell you that. So now, when the value of B is greater than 1, this value over here, when this value of B is greater than 1, what type of function do we have? We say we have an increasing function. Always know that. When the value of B is greater than 1, it could be 1, comma 5. As long as it's greater than 1, it could be 2, 3, 4, whatever. When the value of B is greater than 1, our function is gonna shape like this. This is how our function is gonna look like. Another way to see it, another way to see this, if they ask you, which they love asking this question sometimes, and without using the graph, you won't, let's say you're not given the equation, you are not given the equation, you are given the sketch, and they ask you, is this graph like the very same graph that we see over here? Let's say you are given this graph and there is no equation. So that I get it if they give you the equation and they give you the graph and they ask you, is this graph increasing or decreasing? You're going to say it is increasing. Why? Because the value of B is greater than 1. You will be looking at your equation. But now let's say the equation, it is not given. You are only given the sketch and they ask you, is this graph increasing or decreasing? You're going to say it is increasing. Why? Here's the reason. Without using the value of B, this is how you're going to answer this. Now, again, this kind of involves grade 12 basic kind of when it comes to calculus. Having a look at this, we have a curve. So when you have a tangent on a curve like this, remember a tangent, it is a straight line that touches your curve only at one point, right? So here's one point whereby the tangent and the graph of exponential touch each other. What is the gradient of this tangent? It's positive gradient. Whether you draw, it does not matter. Whether you draw it here or you draw it there, it does not matter. For a fact that, look at the shape. Is this increasing slope or decreasing slope? It is increasing slope. We just spoke about increasing and decreasing gradient, right? The graph, it looks like this. It is increasing slope. So when you have an increasing slope, along the curve, it does not matter where, whether it's here, it's also increasing, whether it's here, as long as you have a tangent like this, as long as it's a positive tangent, just like this, then this curve, we say it is the increasing function. So you're gonna say, we have positive gradient of a tangent. This straight line, we call it a tangent because it touches a curve or an exponential function only at one point. So hence why we say the curve in general, the overall of this curve is increasing function. That's how we say this curve, it is increasing. We don't look at both negative or positive, no. We look at the tangent or we look at the value of B. That's it. Here's another basic, here's another one. What if our curve then it is like this? What if our curve then it is like this? What if our curve then it is like this? Here we're gonna say B, it is less than 1 but greater than 0, meaning it is between 0 and 1. It is less than 1 but greater than 0, meaning it is here between 0 and 1. Just like this, what we see over here, you see this, we have 1 over 2, which is 0, 5. Automatically, if they want us to sketch this graph of G, we know the shape of the graph of G is going to be like this. But one, I'm also giving you from the question referring to the basic. Now, let's learn the basic first. So, if you are given the graph that looks like this, the value of B is supposed to be between this range, supposed to be between 0 and 1. But 1 over 2, 0, 3, 0, 4, 0, 5, as long as it's between 0 and 1, the shape of the graph is going to look like this. And then again, when B is between 1 and 0, we say this graph is decreasing. Now we have a decreasing function. Ne? Again, we can also investigate this by looking at the tangent. Now, looking at the tangent of this, if I draw a tangent, this one is not clear. Let me use the color, the yellow one, the white one. Drawing a tangent here, it does not matter where you draw a tangent. Look at this tangent. It moves like this. It's decreasing the graph. So here we have a negative gradient of what? Of a tangent. We have a negative gradient of a tangent. You see, that's why we say this graph is decreasing if you want to refer to the gradient of a tangent. But if you want to refer to the value of b, if they ask you, is this function decreasing or increasing? You're going to say this function, the yellow function, it is decreasing. Why? Because the value of b is between 0 and 1. Or if you don't want to use that reason, you're going to say we have a negative gradient of a tangent, or we have a negative slope of a tangent. That's it when it comes to this. And by the way, this graph, the blue graph, it doesn't have axis of symmetry. It's asymmetrical, so we cannot cut it or whatever. Ne? All right, that's it on the basics.